Now I can see your screen. And I can see you. Okay, so then we can probably begin. All right, it's now 11 o'clock on the dot. I think we can begin. Good morning, delegates, speakers. My name is Andrew Gill. I'll be the chairman for this forenoon session of the CHPC HPC applications track for the CHPC National Conference. We've got two distinguished speakers who've been long-time users of the CHPC. First up, we have Prof. Ignacio Kukrowski. The professor has been, pardon me a moment. Prof. Kukrowski obtained his MSc degree and his PhD degrees at the Maria Curie Skłodowska University at Lublin, Poland, and he obtained his DSc degree at Nicolaus Copernicus University, Turin, also Poland, and the development of theory analytical protocol, dedicated software, and PC-controlled instrumentation for the study of metal ion complexes by voltammetry. And he spent more than a decade exploring electron density distribution through various molecular systems. And he's authored or co-authored over 120 scientific papers and 7 patents, and he's delivered over 20 plenary and keynote lectures. And today he is going to tell us about, talk to us about, the electron density in covering reaction mechanism. Prof, at this point, I will let you take it away.
All right, so let me start then. Thank you very much for your kind introduction.
Oh, if I may add one thing to the speakers beforehand, I must just ask the speakers, please do not actually post their question until Professor is completely done, because it will disrupt it may disrupt the flow of his talk and so on. But sorry, please take it away, Prof. Professor, I'm sorry to interrupt you at this point, but we are not actually hearing you. Could you, awfully sorry about this. It's a new experience for all of us. If I may ask you, please, to rewind a few steps. We couldn't actually hear you. We could see your presentation, but we could not actually hear your voice.
That I don't know why.
I'm sorry. You are clearly. My sincere apologies. You are definitely audible now. Can you just screen share again, and then we should try again?
So what do you want me to do?
You can now proceed. Deirdre will share your slides and
understanding chemistry using quantum mechanics in study of molecular systems. The use of QM implies an extensive use of high-performance computing. And among 25 members of our group, some became a multi-millionaire or millionaire in terms of CPU hours used. We summed up the hours used by our members, and the figure came up of 10 million CPUs or so. That is equivalent to running 47 nodes in 1 year, 24/7, continuously. Or otherwise, considering our involvement with CHPC, it is equivalent to 15 nodes for 3 years, 24/7, continuously. And this is just on top of our local in Pretoria facilities and nodes described here, which are used mainly now to run AMOL software to get IQA, QTM data, in addition to our own software applications when we develop new methodologies. We use CHPC for classical computational jobs performed in Gaussian to obtain the indicated outputs like spectra, structural properties, optimized structures, transitional state structures, and so on. But importantly, in addition to this, we request Gaussian to generate for us formatted check file or wave function file that are used as inputs to AMOL or our own applications indicate here on the left. We use HPC and our laptops or small resources daily. Our aim is to explore IQA as much as possible, and our hope is that AMOL software needed to obtain IQA data will be installed at CHPC very soon. If this happens, then sky will be only the limit for what we plan to do, and also our own resources will be used mainly to analyze electron density-based data generated by CHPC, as well as for the development and testing of new theories and applications. Here we show the examples of publications published in the last 10 years, 5 papers on average per year, and the most often journals, high-impact journals in the field we published in. I'm sure that you all know Dr. Krishna Gavande from CHPC, and I am very proud to let you know that his research career started in my group as an MSc project, and he has done an excellent job as justified by the indicated publications that were published in the leading journals in the world from just the MSc project. Let us focus on our research interest, that means the electron density and its distribution throughout a molecular system. And this is because electron density is unique for each molecule, and it carries all information you need to explore and quantify properties of molecules. We explore electron density extensively using commercial and our own applications with an aim to uncover and understand the nature and the strength of interactions, chemical bonds, to understand the chemical reactivity, direction mechanisms, why bonds are formed or not, to understand relative stability of molecular systems such as conformers, classical metal complexes, organometallic compounds. Let us start with relative stability of conformers of Proline that acts as a catalyst, as you will see soon from slides that follow. There are two conformers, the high energy conformer, 1B, and the low energy conformer, 1A, and the latter is about 7 kilocalorie more stable. Well, the energy data are obtained directly from Gaussian calculations, but it does not explain why this is more stable than that. Classically, one would look at the differences in structure, and we see that H5 is pointing up, whereas it's pointing down in the low energy conformer, and the atoms involved in the hydrogen bond are much closer in low energy conformer, and this is typically used to explain why this structure has lower energy than the other. However, we go much further and deeper by employing our FAMSEC approach that is based on electron density, because it's making use of the energy term computing in IQA, which in turn makes use of density distribution within atoms defined by QTAIM, which in turn defines the shape of atoms based on properties of electron density. So there is an entire package that is making use of electron density distribution throughout a molecule. Let us consider a transition from higher to low energy conformer in order to understand why this is indeed, why this is low in energy. And we start with a typical two-atom approach, as classical chemists would do. So we look at H17 and N13 that form the hydrogen bond. And we computed the interaction energy between the two. Data on the left refer to high energy conformer, and on the right to the low energy conformer. And what we can see that interaction between these two atoms is much stronger by 33.5 kilocalories in the lower 1A energy conformer. Furthermore, we established that the nature of this interaction is mainly of Coulombic nature, which means the interaction due to the difference in charges between the two atoms. And this is because the term computed for V classical is much larger than the other component of the interaction, Vxc, which refers to exchange correlation term or degree of covalency. However, these two atoms are not only the only one, but not even interacting most strongly. This is the C14 and N13 that interact 50 kilocalories more strongly, and more favorably this takes place also in lower energy conformer. Finally, it is important to stress that there are 136 interactions. So one mustn't just look at one or two. What can you learn from all of them? Well, in a first attempt, one can summarize all the interactions together, and we obtained that all interactions in the lowest energy conformer are nearly 50 kilocalories stronger than 1B. All interactions also involve the covalent bonds that are seen here as the solid lines linking atoms. And we computed the strength of the covalent bonds, and we found that they are nearly 40 kilocalories stronger in 1A. Considering changes in the strength of covalent bonds is beyond any classical chemist. Nobody would even bother to consider this. However, FAMSEC also allows to estimate or quantify even how good or bad the molecular environment is for a particular atom. And for that purpose, we use the interaction energy between a specific atom and the rest of atoms in a molecule. And this energy term is negative, that means favorable, for 11 out of 17 atoms in the lowest energy conformer. We go even further. We can identify which atoms enjoyed the molecular environment most, or otherwise. But looking at those that enjoy the most, this is the nitrogen, carbon of the carboxylic group, oxygen, and hydrogen of the carboxylic group. So what it means is that we can identify molecular fragments that become stabilized the most when going from higher to the lower energy conformer. Well, there are many more possibilities that one can consider. There's no time to do for all of them. These are just few examples. But the lesson to take home from this is that even a small structural change, up, down, slightly or sort of shorter and longer distance, resulted in an enormous energetic changes throughout entire molecule. Let us now focus on the reaction mechanism. And this is what you see is a classical scheme published by at least 20 years ago for the Proline catalyzed aldol reaction. As you can see, this acetone here reacts with Proline, goes through many stages, picks up a aldehyde that gets involved, gets attracted, it is being bonded somewhere, few things happen, and eventually the catalyst is being recovered, and the acetone and the aldehyde are bonded now and formed a new compound. That's the purpose of this process. Well, it is a nice pictorial story of assumed events taking place, but it does not provide any in-depth explanation. So we are making use of REP-FAMSEC methodology published last year by us, and due to the time constraint, I just will focus on the first stage of the proposed reaction and mechanism. This is the first stage of the process proposed by Liszt, and it turns out that it is made of several steps where chemical changes occur. Steps from 1 to 6 describe CN bond formation, the first proton transfer and the new OH bond formation, whereas steps 6 to 10 describe the second proton transfer. It requires these two reaction energy profiles computed for the enthalpy change and the free energy change. In this case, they require some additional explanation and clarifications. So the blue trace is computed for the low energy conformer and the red one for the higher energy conformer. Instantly you can note that these trends are opposite, whereas the high energy conformer decreases the energy, which is a favorable trend as the energy of the system decreases. Just opposite is observed for the low energy conformer. In addition, the energy barrier of 35 kilocalories per mole would have to be overcome by the low energy conformer, and this is absolutely prohibitive. It implies that only the higher energy conformer, high energy conformer is the active catalyst in this process. We made use of our Rep-FAMSEC method approach to explain each step along the reaction pathways. However, to conclude my presentations, I will discuss only the very first step when the adduct formation occurs. And in this case, what you can see, there is a significant decrease for adduct containing high energy conformer in comparison to the lower energy conformer. One must understand that to form an active complex on adduct, that these two molecules have to get involved in attractive interactions. We quantify them, which means we computed the sum of intermolecular diatomic interactions energies for all unique 170 atom pairs between molecular 1 and molecular 2. And we found the interactions to be stronger by minus 19 kilocalorie per mole in the case of the higher energy conformer. That goes very well with the observed change in the energy. Also, we computed all possible interactions in these two molecular systems. That means inter and intramolecular interactions. And also in this case, we note that these are more favorable for the higher energy conformer containing adduct. This again goes very well along the observed trend in the reaction energy profiles computed for the two molecular systems. When we do IQA calculations, we obtain all possible diatomic interaction energies. And we can then analyze them and select atom pairs that are involved in the strongest interactions, say in absolute terms above 10 kilocalories per mole, larger than that. Then we can group those atoms into meaningful molecular fragments, like here G and H. These two molecular fragments play the most important role, and their role and significance, what they do, is being monitored throughout entire process of the reaction mechanism. It also means that the atoms that are not involved in strong interactions like these two methane groups on acetone, just act as spectators. We don't have to worry about them. We can just focus on these two groups. Hence, focusing on them, we computed the interaction energy between all of the atoms of these two molecular fragments. And again, not surprisingly, maybe, we found that these interactions are by far more favorable in the adduct containing higher energy conformer. Clearly, fragments G and H drive the adduct formation, and they are informing the strongest interactions in both adducts. The combined Rep-Famsek approach can provide so much information about the chemistry, chemical process, and so on. However, I have to conclude my presentation, and let me state the following. The reaction energy profile computed for the assumed reaction pathway can be used to support or reject the proposed mechanism or hypothesis related to the reaction pathway, but still does not provide a sufficient insight. A combined Rep-Famsek approach is of general nature, as it allows explaining not only reaction energy profiles for any reaction mechanism, but also, among others, we can explore relative stability of compounds. Here we've done for the Proline conformers, or relative reactivity of compounds, and here we examined catalytic activity for the two conformers, and we found that high energy conformer is the only catalytically active compound. Finally, I would like to state that without CHPC support and facilities they provide, productivity of a research group, that means number and quantity of graduate students trained, number of papers published, standing of research groups considered internationally or even nationally, would decrease immensely, or even no significant computing could be performed. Let me close my presentation by a few acknowledgements to my PhD student, Mr. George Dimba, and my collaborator, organic chemist, Dr. Darren Riley. The financial support goes to the National Research Foundation of South Africa and organizers of this conference. Thanks a lot for your kind invitation. Finally, to all the staff of the CHPC, thank you very much for your hard work, and in particular to Dr. Lopez, our immediate contact with CHPC, and Dr. Gavender.
Thank you much, Professor. Very much, Professor, for your presentation. And apologies again for the technical troubles in the beginning. Let's have a look if there are any questions now. So Quinn Reynolds has a question. He says, thank you very much, Professor. Great insights. In your opinion, what are the biggest performance barriers in modern electron density modeling methods of HPC systems? What do you think needs to be done to allow us to reach the next step in terms of larger molecular systems and improve computational performance?
Well, the methodology used here implies using interacting quantum atoms approach, and computing data within that energy partitioning scheme takes a lot of computational power. So what it is happening now, hopefully, the software that we are using and we have license for is being installed and hopefully will be finished installation soon on CHPC clusters. And that will allow us to go for much larger molecular systems that then we can analyze. Just, I don't know if it's of interest, I can mention that if the molecule contains, say, about 100 atoms, computing energy terms required might take 3 days using a cluster of 4 nodes. So it's really a demanding computational protocol.
Thank you, Prof. We've also actually now answered the question, I think, of Afra Kerala, who was asking exactly how long it took to run and what computational resources. So thank you very much. You've actually in the event answered 2 questions. And so then the last question was from Stefan Kutsia, who said, "Hi, Prof, excellent talk, and wanted to know if the calculations were open shell. Is it viable to do these analyses if geometry optimizations are not possible?"
At this stage, we have permission of the owner of the developer to make access only by our group. To make access by other students, CHPC would have to purchase the license from the developer of AMOL software.
Okay, thanks. And regarding the question of whether it is open shell or not, whether the calculations are open shell?
I see that Stefan asked another question. I don't know if I can comment.
Yes, please do. Please do. Can you hear me, Prof?
He said, and would it be viable to do these analyses if geometry optimizations are not possible? Well, if you are interested in interaction energies in the optimized system or for the optimized, obviously then it's not possible. However, if you want to consider a particular geometry of a system, you can perform single point calculation on that structure and either run the full computation of IQA, or you can select atoms of interest only. So you can select atom pairs for which you calculate interaction energies.
Thanks, Prof. Okay, I'm afraid we've run out of time for questions. We're actually slightly over time, again, probably because of the technical delays in the beginning. So I'm going to introduce our next speaker. Thank you again very much, Prof. Ignacio.
Thank you.
I'm now going to introduce our next speaker, Dr. Maz Bamji. And he is a senior lecturer at the Department of Mechanical Engineering Science at the University of Johannesburg. He lectures first year engineering design modules, but his specialization is in various different aspects of fluid mechanics and heat transfer, specifically computational fluid dynamics and biomedical applications. Prior the use of the Navier-Stokes and Lattice Boltzmann based computational fluid dynamics approaches in multi-scale fluid dynamics, heat, mass, and transfer problems. He's going to talk to us today on the subject of HPC as an enabler for growth in computational fluid dynamics research. Maz?
Thank you, Andrew.
Welcome. Yes, thank you.
Sure. Can I go ahead and share my slides?
Yes, please.
Perfect. Okay, just want to confirm that they are reflecting. Are they reflecting?
Yes, they are. Thanks.
Awesome. Thank you. Okay, thanks, Andrew. So my talk, as Andrew has said, will be on how HPC has been an enabler for growth in computational fluid dynamics research. I'll sort of give an overview of how that has happened within our department, which is the Department of Mechanical Engineering Science at UJ. So overall, give you a bit of an introduction, which will give you a bit of context on CFD research within our department. I'll just discuss CFD in a nutshell and the need for high performance computing as a consequence. Overall typical HPC workflow that we utilize, an overview of some of the codes that we use, and then I'll go through some of the select or a few select projects, an overview of some of the key results, outcomes. We'll also discuss some of the challenges that we've also faced, and then ultimately just conclude. So computational fluid dynamics research conducted in the Department of Mechanical Engineering Science at UJ has become really prominent over the last few years. I know when I started as a master's student, our lab for CFD and FEA was sort of like about 2 computers, reasonably high performance at that time. And by high performance, we meant a multi-core with a bit of RAM and a graphics card. And that's evolved significantly since and has led to greater productivity. And the CHPC has played a key role in that. Now, the primary purpose is for me to highlight the need for and the benefit of HPC to enable and grow critical and relevant research in this broad area. The use of CFD and HPC has grown significantly over the years within the department, again, largely due to the acquisition and provision of HPC platforms. And by that, I mean, we've acquired a lot of our own HPC platforms in the sense that we've bought a lot more computational servers, and I'll put that in inverted commas, for access to both staff and students, and then obviously through the HPC, and we're still looking at growth within the department and other platforms that may benefit us as well. Now, just an overview of sort of CFD research conducted in the department ranges in applications, for example, process and engineering and separation processes, something I'm heavily involved in, solar air heating, atomic layer deposition. We even have some biomedical applications happening, and these are just a few amongst many others. In terms of CFD in a nutshell, and this is really CFD in a nutshell, we obviously have our Navier-Stokes equations, which comprises of the continuity equation, which is sort of conservation of mass. And then we have 3 other transport equations, which is our conservation of momentum. Now, in CFD in general, we sort of would rewrite these equations into a generalized scalar transport equation. And this scalar transport equation is then solved on a discretized domain. So for example, I gave an image here of a hydrocyclone, where we took a hydrocyclone and we discretize it into cells or voxels, and then we numerically are solving that specific generalized scalar transport equation on this computational grid. And obviously we have one transport equation for every variable that we're solving for. In other words, if we add additional physics, such as heat transfer, multiple phases, if we start accounting for turbulence or chemical reactions, we start to add additional transport equations that need to be solved. And again, many of these problems require multi-physics modeling approaches, and coupled with exceptionally fine meshes, so we go sub-millimeter, and then really small time step sizes on the scale of or far below microseconds. As an example, this hydrocyclone simulation is about 5 microseconds time scale with a minimum of 2 seconds. So we have quite a lot of time steps that need to be solved, but then we also have to iterate to convergence on every time step, and we have to solve the equations on every cell. So therefore, we really do have a significant need for high performance computing resources. We need this to execute meaningful simulations in these research areas. Now, let's look at our typical HPC workflow. So I'll talk about pre-CHPC and with CHPC or other HPC platforms. So as I said, in the past, we would do all the steps, pre-processing, which would be the generation of the geometry, the mesh, the setting up of the physics, initializing the simulation, then the processing, which is carrying out the actual calculations, as well as post-processing, which is looking at the results and analyzing the results. All of this was done on, again, high-spec desktops. And the major challenges we had with this approach was obviously slow to no progress on extremely complex problems due to very slow runtimes. And we'd often have to leave out detailed yet critical physics, or to scale it down at least. Right. And mesh-independent studies then became difficult to impossible, which does impact academic research and postgraduate studies. And then again, resource sharing in large groups became a major problem because everyone needs significant time on the machine, which is not always easy when you have machines that are running simulations relatively slowly. Once we've changed over to once we got access to the CHPC as well as other HPC platforms, we started re-looking at how to change this specific workflow. And then we agreed to pre-processing, and the post-processing stage would then occur on desktops in the lab, right, which is our servers that we have in the lab. And that would be based on shared time. Each PI for their project decides how they want to share their time. And then the processing itself, we started to move to the CHPC or the HPC platform. And there's multiple benefits that we've seen through this approach. The first is obviously naturally faster runtimes because we have more computational resources. Those detailed or critical physics can be included and accounted for. And regularly we start to increase the amount of detail in terms of the physics that we include in our models. Mesh-independent studies have now become routine, and which is natural and the appropriate process for academic research and postgraduate studies. And then resource sharing has become improved because obviously a student or a staff member, a researcher in general, would need much less time on the machine for pre-processing as well as post-processing. In fact, many are now doing some of this on their laptops. And the processing then goes to CHPC. So there's much less time needed on the machines in the lab, which allows us to carry out many more simulations. So also a researcher could have one running on the CHPC while preparing a new simulation or tweaking a simulation or even analyzing results from a previous run. We still have some challenges, and this is less to do with the platforms themselves and just more to do with personal aspects, right? So the first aspect is overcoming the initial inertia from new users. So new users are very much familiar with GUI type structures. I call it the Windows syndrome. We're very used to everything being very GUI. And having also physical hardware access. And I'll talk a bit about this in context of COVID as well. This concept of having physical hardware access. So more needs to be done to acclimatize new users, one, to the command line and remote server use. A perfect example of this thing of having to have physical hardware access is right now in COVID, what I did is I managed to take my servers with me home, so that my postgrad students still had access. And then we managed a really nice resource sharing strategy. Instead of, you negotiate between each other and decide who's going to be in the lab when, I built a simple Google calendar, which was shared, and everyone gets up to maximum 12 hours on the machine at a time. And they use a secure remote connection to the machine. They still have a GUI remote connection, but there's still a lot of struggle with managing that remote access because of not having the physical hardware available. So it's a two-pronged problem with new users, is having access to a GUI versus using the command line. And then the other part is also just having to use remote access versus having physical hardware access. So that's our typical HPC workflow. Just to give you a bit of an idea, when I talk about these typical high-end desktops that we have in a lab, the setup we generally have is we usually have Xeon or Core i7 processors, anywhere between 4 to 6 core variants. Admittedly, we don't turn off the hyperthreading for these machines. Then it usually ranges between 16 to 64 gigabytes of RAM, 2 terabytes plus storage space. Storage is an important aspect of CFD. We generate quite a lot of data. There are some unique machines with Tesla GPUs, which for specific CFD problems may be useful, where we have, for example, coupled particle simulations. And there's at least one machine where we're currently using the AMD Threadripper. I must admit that's looking quite promising for quite a few problems already. So in 2009, when I started as a master's student, we started with one lab and about 2 or 3 such machines, obviously scaled down from what you're seeing here. As of 2020, we have at least 2 of those labs with close to 20 machines. And as a result, the research capacity has grown significantly. And funny enough, it has a lot to do with having access to an HPC platform, because being able to produce more research allows for more funding, which you can pour back into your private infrastructure. We're also currently exploring greater use of a data center at UJ. So ideally, this would be a containerized environment whereby we can have unique environments based on the application. So I've just had one built for me where it will be running CentOS to run all our applications, CentOS being the best middle ground for all the softwares, both commercial and open source for us. Speaking of the codes, in terms of commercial codes, we have ANSYS Fluent, ANSYS CFX, and Star CCM Plus, as well as Xflow. Xflow being a Lattice Boltzmann-based solver. And then in terms of open source codes, we tend to use a lot of Palabos and OpenLB. So as I said, the first 3 codes are continuum-based. In other words, we model the fluid as a continuum. At the macroscopic level, and we start off with the Navier-Stokes equation. Whereas Xflow and the open source codes are a bit more Lattice Boltzmann based. In other words, we model the fluid from a mesoscopic perspective. In other words, it's sort of between molecular dynamics and the continuum approach, where we're solving the motion of and collision of particles on a defined lattice grid. And then we macroscopically average these physics to recover continuum-like behavior. And in many ways comparable, because we do recover Navier-Stokes behavior, but there are some significant benefits in terms of computational efficiency, as well as significant benefits in terms of recovering some of the smaller scale dynamics. Just a quick one, I managed to run a simulation akin to a continuum level simulation on a laptop, but the continuum level one had to run on the CHPC. This just gives you a bit of an idea of the efficiency gain at times. Now, just a brief overview of some of the problems that we've tackling. For example, modeling of multiphase flow in process equipment. Really, the aim of this project is to develop accurate and computationally efficient models, whereby we capture complex multiphase flow interactions in process equipment, such as hydrocyclones and fluidized beds. The image here shows us particles entering and accumulating within a hydrocyclone, which is used for separation of minerals or cleaning of fluids, etc. Often here we would use coupled fluid dynamics and granular dynamics to solve the problem, and we model these multiphase flow interactions. In this, we use both Navier-Stokes and LBM-based methods, and we also look at the accuracy. In other words, we want to benchmark to experiment, but we also benchmark computational efficiency on many levels, because we want accurate yet fast models that in the future industry can use. Again, we would want to use this in the future to investigate design changes. Right, so this is just some examples of what we've seen from there, some citations from our papers or publications. This, for example, shows the velocity magnitude in the hydrocyclone from an LBM as well as a Navier-Stokes-based model. You can see very much recovering the same physics, but when we look at the performance, and that's the number or million cells updated per second, if we use that as a performance indicator, we can see that the Lattice Boltzmann is almost way over 10 times faster than the Navier-Stokes ones due to various reasons. Then we have another one, which is based on a master student study, which is looking at heated fluidized beds. Similarly with the hydrocyclones, able to investigate on very fine grids VOF, mixture model, Eulerian type multiphase flow models to predict the air core surface. Again, this allows us to understand the greater underlying physics. We've gained a lot of publications outputs. You can see one doctoral graduation, which was actually myself, and then at least 3 master students within the last few years. It's been tremendously productive. And we've also built an industry collaboration through that with a process equipment manufacturer, because they are interested in this research. We can use quite a lot of models in terms of the multiphase, volume of fluid, mixture, Eulerian, some granular models, discrete phase, discrete element method, dense discrete phase, and the lattice Boltzmann. We typically use about 5 to 10 CPU nodes on the CHPC with about 24 cores each. And we use up to about 120 gigs of RAM. And our sims tend to run about 4 hours to 4 days continuously. Obviously, once it hits the 2-day mark, we would have to restart it at the last save point. Just an overview of some of the group members. I won't go through that in detail. Another really useful project that we're working on currently right now is Cern's Atlas ITK upgrade. We were tasked with doing the nitrogen purging and humidity simulations in the ITK. So we want to understand the need for local versus global monitoring of the dew point. The dew point is particularly important because we would be worried about condensation within the strips region where our detectors are. We're going to be moving on to the pixel region as well shortly. This just shows some of the simulations in a nutshell. We used fluid flow coupled with heat transfer, and then species modeling to model the nitrogen and air mixture for when we account for leaks into the domain, and then also humid air leaks. So we obviously recover a temperature field or distribution and a relative humidity distribution. And from that, we can then, using a specific formula, we are able to then recover a dew point and to assess where that dew point sits, and if we are concerned about condensation or not, and if there needs to be design changes, or what is the maximum leak rate that the design should be designed for. Again, so we've completed some initial models, and we're currently adding complexity and integrating the pixels, as well as optimizing the intake manifold. So quite a few things going on in this project. I've talked about the models that we use. We also don't just model the fluid, we model the conduction through the thicker walls in the region. And we have models on the scale of about 5 to 30 million cells. Again, the resource use is a lot like the previous one, except we usually stick only to 5 nodes. And our 3D models usually about 2 hours. That's going to change, I think, though, as we add the pixels and additional geometrical complexities. The major obstacle we've had on this problem is the simulation does require manual convergence steering and numerical relaxation. So we regularly need to stop and alter it, which isn't ideal on an HPC platform. So perhaps we should look at some machine learning to automate this convergence steering. It's perhaps something we should think about for the future. Again, this is a cross-institution project which involves UJ, UWC, UNISA, and we also have some partners over at SLAC National Accelerator Laboratory in Stanford University. Okay, and then the last project I'll summarize is one of the benchmark projects at UJ, which is the atomic layer deposition. It's really about understanding the fluid dynamics, chemical reactions, and heat transfer in the process of developing ultra-thin film for future technology. And we look at how the backward-facing step phenomena affects the fluid dynamics, and in turn, the chemical reactions, and therefore, ultimately, the growth rate on that thin film. And ultimately, we want a uniform growth rate across the substrate, which is at the bottom surface here. This again just shows some examples of how we look at the fluid dynamics. We look at the topology of the flow. For example, we look at stagnation regions, dynamic contact lines, etc., and how that in the end affects the growth rate. Again, over the past couple of years, this has resulted in 25 international peer-reviewed journals, 35 conference articles, and about 7 postgrads, 3 of which were PhD theses. Again, we use a lot of CFD, density functional theory, and some molecular dynamics with Shemkin Pro coupled to ANSYS Fluent for the chemistry. Again, typical resources, about 6 to 10 nodes with 96 gigs RAM for each node, about 3 to 7 days runs for 2D model, 3D models about 7 to 14 days. We're also looking at applying some LBM to these problems for recovering some of the smaller scale fluid dynamics aspects. But again, the whole model and the sequential process of purging, etc., through this is run by using a user-defined function and a journal file. So that alters the pulses and purge sequences in the model, because it's not something you can traditionally do within Fluent directly. You have to write a custom routine for it to change the pulse and purge sequences. Again, this is quite a large group where we've just commissioned this week a state-of-the-art ALD experimental facility, which will help grow the research further. As you can see, we've got quite a few members in this group, from Prof. Jen, who's the PI. I'm a collaborator, quite a few PhD and master's students, as well as undergraduate students involved in this research. And just to conclude, within time, really, we need more power, and we won't say no if offered. Andrew's laughing because he knows I'm always asking for more.
Noted.
I had one student who who was proactive and without asking me went and contacted Andrew and Charles a few years back and said, I need more resources. This is not enough.
Yes, thank you.
So, okay, that's it. If there's any questions.
Thank you, Lars, for an interesting talk. Let's see. There's already a question. I bet it's from Quinn. Quinn always asks the best questions.
I've got one from Charles, if that's okay, and I'll go for that quickly.
Oh, yes, perfect.
So, Charles, we have been running our LBM stuff on your CHPC. we did discuss it a while back. I actually promised you a wiki page, and I need to build it. But essentially for the Palabos, it's just a really small library of C++ code. So we would run it much like a C++ code, but we use the OpenFOAM sort of environment. So our job files would look a lot like an OpenFOAM one. I think since the migration recently and changes in the cluster, some things aren't gelling as well. So I will be in contact with you to get some of those aspects fixed. But we haven't installed it directly. In the past, we've just installed it, sort of like left the folder in our local user repository, and then ran it much like we would run OpenFOAM. So I think that sort of answers that, I hope.
Okay, thanks. And then Quinn Charles actually beat Quinn to it this time. So Quinn says, yes. Thanks for an excellent presentation, Mars. It's good to see so much computational mechanics research being done. Given the huge performance advantages, do you think lattice Boltzmann methods will eventually replace traditional finite volume-based CFD solvers? Or are they likely to remain horses for courses?
This is really such an interesting question, but it's one that's been asked so much. One, it's still a niche area in some ways, but gaining significantly greater traction. I will say that it has serious potential to not necessarily maybe replace it, but to become just as commonly used. We're seeing a greater advent of commercial-based packages. Xflow is one of them. I do find it's not a criticism. It's just lattice Boltzmann, as much as it's been covered for many years, is still not as mature as our finite volume solvers. So multiphysics is still the biggest barrier in my personal perspective. It's been the hardest part, but those are being overcome. Again, it's still a lot of the good flexible codes are a lot of the open source ones, in my opinion. And as a consequence, it means a lot of coding. So for users who are understanding of the numerical methods and the general physics, but are not good at coding, it becomes a bit of an issue. Whereas the finite volume solvers, there's quite a lot of GUI-based ones that have a lot of flexibility and quite a wide range of applications. But I do see it coming forward, and I do think we're going to see a lot more from it in the future, especially with the advent of some of these really good commercial codes that we've been using as well. I think once multi-physics becomes a bigger part of that, we'll really see it grow more.
Well, thank you. That then touches on the last question, which is from Ollie Oxterby, and he was asking about the caveats regarding, so an obvious one is what you just mentioned, the multi-physics.
Yeah.
And then are there any other things one has to be careful of about these?
So boundary conditions have to be treated very, very carefully. Also, solver stability is a very important part. Just like we have our CFL condition in finite volume solvers, Lattice Boltzmann method comes with their own stability criterion, which is a little bit more intricate because you have to have your lattice scales and your physical scales. So we work on meters, but then you have to convert it to the lattice dimensions, and you have to work between those to get that stability right. That's one of the issues. But yeah, and there's good talks about that, and it's been covered quite a lot, because that's a question a lot of people are asking about, is stability, but also conversion between the lattice dimensions and the physical dimensions. The main reason for the performance of the Lattice Boltzmann method is just that it's so much more parallelizable. Because remember, you just have particles moving on a lattice, and they move in defined directions. So they have a stream and a collide. So if I have a particle in the center of my lattice, it can only move up, depending on even how many lattice nodes you have, but it would say move up diagonally or to its sides or down, right? So it only has discrete directions it can move in. And once it gets to a new lattice node, it either collides with a particle that's there or it stays there. And if it collides, it goes back to its original place. And it's just literally tracking these particle distribution functions, literally. And it makes it just a lot more parallelizable. However, the more you add certain types of physics, then you start to see that become a bit of an issue. And then that parallelizability starts to diminish. So for example, on the multi-phase problems we had, it was really great on the single phase flow. As we started adding in the volume of fluid, we started to see the performance diminish, and we were struggling to maintain the air core, right? Because of stability for high Reynolds number flows. But then once we added the particles, because we were then modeling surging where the air core disappeared, then we were able to get really fast performance again, because there's no more VOF being solved. And we were able to do it really quickly, because now we have the fluid, which is particles, and the particles, which are particles. And it's just so much more parallelizable. So I hope that sort of answers that question.
Thanks. Yes, that was very interesting for me too. So we have one last question from Quinn, and he's asking about using HPC and CFD in undergrad. I think this has to be the last question.
Yeah, so this is important. So we've got a lot of our undergrads who are starting to really get into the fluid dynamics and the FEA stuff. And obviously they're starting to encounter problems that need more performance. We did upgrade our entire fourth year lab, which now at least has Core i7s with 8 gigs RAM and decent graphics card. More of our undergrads are looking at, using our bigger servers. And we even have, especially on the ALD side, some undergrads who are starting to move into the CHPC usage, which is a really great thing. I think it's brilliant. I've been talking to our ICS division. We've been looking at the data center as a means of including HPC as part of our undergraduate education. It'd be a great platform to work on directly at UJ. The CHPC workshops, we do send them out. We know they are tailored to postgrads, but we do find a lot of undergrads starting to say they're interested in it. So I think the undergrads are definitely interested. So we will be looking at bringing it in. I know in the past we used to have the CHPC used to have the cluster comp that often used to engage quite a lot of undergrads. I don't know where that is now. But yeah, I think we still do. There's a lot to be done to grow it though. It's definitely coming in, but there's a lot more to be done to grow the use for undergrads and to tackle this GUI effect. and also the physical hardware effect, being able to work command line and on remote resources. I think though undergrads are becoming a little bit more open to it. They're used to using cloud storage. And if you're able to use cloud storage, then it's like, okay, this is like you're using cloud storage, but you're just doing cloud computing. You're not just storing data, now you're generating data in essence, in a similar manner. So I think we are starting to see positive strides that way.
Thanks, Mars. It seems like we're out of time now, so I'm going to thank both you and Prof. Kukoski for very interesting talks and for participating in our conference despite all of the difficulties, lockdown, and technical difficulties and stuff. Thank you both very much.
Okay.
And that concludes the session.
Yeah, and thank you again for having us.
Pleasure.
Thank you very much, Andrew. We will now be taking a short break, and we will then start our next session, which starts at 12:15.
Thanks,
Thank you. Bye.
So the video stops sound.
Bye-bye.
All right, it's 12:15. I'm gonna be starting. Good afternoon, everyone. My name is Zintle, and I'll be chairing this session for today. We've got two speakers on this session, and the first speaker will be Professor Babatunde Abodin, who's from University of Cape Town. And the topic he'll be talking on is under the development and application of climate models over Africa using the CHPC. Over to you, Professor.
Thank you very much. Let me share my screen. Please, can you confirm if you can see my screen?
Yes, you can see your screen.
Okay, thank you very much. Good afternoon, everyone. My name is Babatunde Abiodun from Climate System Analysis Group at UCT. So I want to thank the organizer for inviting me to this conference. I will be talking about the development and application of climate models over Africa using the CHPC. Interestingly, our group is one of the long users of the CHPC machine. We started using the machines since 2008. Today, I just want to give a brief overview of how the CHPC has helped us in developing and applying climate models over Africa. So this is the overview of the presentation. First of all, I will start with a brief introduction to atmospheric modeling. Then I will talk about, I'll then talk about the model that we have been developing in the group. The name of the model is CAMULAG. Then I will talk about other models that we also been applying to investigate different topics or doing different research projects in the group. So this just to provide highlights of this, some of the results. Because of time, I won't be able to go into details. So talking about atmospheric models, they are important tools for understanding the different, the complexity of the atmosphere. And is because it helps us to predict to simulate the past state of the atmosphere and also to predict the future state of the atmosphere. As a result of this, is becoming a tool for providing information for the policymakers on how to take some decisions. So, but what are these models themselves? Well, they are simply system of differential equations that are derived. Those questions are derived based on the physical laws of fluid dynamics and chemistry. So these are just examples of this the equation. Basically, it contains things like zonal the momentum equations, the hydrostatic equation, the continuity equation, mass continuity equation, the thermodynamic equation, and the equation of states. So we try to solve these equations with the aid of a computer. So the way it works is that we divide the entire globe into three-dimensional grid, and we apply this equation on each grid point, and then we solve those equations each grid point, and also see how they interact. In addition to this equation, we also have some processes that we have to solve at each grid point, things like solar radiation, the heat flux, the surface hydrology, the cloud processes, and so on. So there are a lot of equations to compress together, to crunch. And that is only possible with the help of high performance computing. So one challenge that we face with climate modeling is the issue of model resolution and atmospheric processes. So we have different ranges of circulations in the atmosphere. Different circulations they range from maybe about less than 2 meters, things like small turbulence eddies, up the way to more than 5,000 kilometer long waves. All these processes interact together in a complex way. And for us to do a good job, we need to resolve all of them. That means if we have, if computer has infinite power, we will need about less than 0.5 meters covering the entire globe to resolve all these processes and their interaction. But we know that is not possible. So at this present, so what we do is to actually find a compromise between choosing the resolution that we know that our computers can take and the area that we want to simulate. And that has led to different types of climate models. So we have some global climate models. These models cover the entire globe, and they try to simulate the entire atmosphere, but at a low resolution. A typical GCM has resolution about 10 kilometers. And with that resolution, things like some of these processes will not be resolved. Things like a thunderstorm, land sea breeze, all these processes will not be captured by those models. That means we have to find another way of parameterizing those processes. So in order to solve this problem a bit, we can use a regional model. Unlike the global model, the regional model focuses on area of interest. For example, it could be West Africa, it could be South Africa or East Africa, but it will use a higher resolution compared to what GCM will do. So for example, a typical regional climate model could have resolution of a grid size of 5 to 50 kilometers, depending on the computer resources, but it will focus over a region. The downside of this type of a regional model is that it only sees what it sees atmospheric processes within its region, within the region of focus. It doesn't know what is going on in the surrounding. So if an atmospheric process is coming into the domain, it doesn't see it. So the only way of introducing those atmospheric processes into the model is actually to force the regional model with simulation from a global model. So, which means the global model will resolve the large scale features at a low resolution, and then we use the result to force to provide a result for the regional model at the boundaries. But the caveat, the problem with that is these are two different models with different solutions at these boundaries. So the solution may be conflicting, and that normally leads to the boundary boundary condition problems in many regional models. Here is an example of how those boundary condition problems. Here we have this global model nested with the regional model. Based on these calculations of the region of the global model, it could feature a general flow moving from west to east. But because the regional model has a high resolution, it could feature a small scale system that actually is moving in opposite direction. So at the boundary, we have to impose the result of the global model on the regional model, which may conflict with what the regional model is wants at that boundary. So, and here we also see a conflicting results at the other edge. So what normally happens with that is we have like a convergence flow at the boundary, and that convergence flow will lead to upward motion, and upward motion will produce precipitation. This is the erroneous precipitation because of the imposed boundary condition. And this is just an example of that kind of precipitation. You see here that this is a precipitation field. We have this large amount of rainfall here, which is an artifact of the boundary condition model. So a typical regional climate model will have this, either it has an excessive precipitation at the boundary, or the boundary could be very clear as a result of divergence there. So it's a problem that is ongoing and still struggling to find a solution to it while using a regional model. However, there is a third type of model, a third approach. And the approach is actually to use a global model that has capability for stretching. Sorry. So invariably, it's a global model, but it has capability to increase the resolution locally over the region of interest. Here is an example of such a model. So we have this global model. It increases the resolution over the region of interest so that it can resolve the local scale features better. So, and the model we are developing is in this category. So it's called CAM-ULAG, and it's a global model that has capability to increase its resolution locally. There are two approaches with this grid adaptation. We call that stretch grid adaptation. There are two approaches we normally use. First, it could be a static grid adaptation. In this case, the model focuses the high resolution over just an area, and that doesn't change with time. So throughout the period of resolution, a particular region of the world, we have that high resolution to simulate the regional scale features over that area. The other approach is what we call dynamic grid adaptation. With this approach, the grid is the location of the high resolution of the model is changing with time, depending on the atmospheric feature of interest. So for example, if it's stimulating tropical cyclone, then the grid, the resolution of the grid will be changing following the location of the tropical cyclone. I will show an example of these two approaches later in the talk. Then the first one, just want now to go into the development of CAM-ULAG. This has been well documented in the first two papers, and we have applied it to look at different atmospheric problems, both over West Africa and Southern Africa. So the CAM-ULAG, which we developed around 2008, 2009, we developed it by coupling two models. We did it by coupling the ULAG. ULAG is a dynamic core developed by Smolakevich since in 2005. So we introduced this dynamic core into the community atmospheric model called CAM. So in order to take the advantage of the grid adaptivity that ULAG has. So basically it's a CAM-ULAG, and which is where it got the name from, is a coupling of community atmospheric model and the ULAG dynamic core. These are the fundamental equations in the model in tensor form. So we have the continuity equation, then we have the momentum equation, then we have the equation for potential temperature, then we have one for moisture, be it cloud, be it cloud droplet, rainfall, and so on. So we have prognostic equation for all the scalar variables in the model. Then the grid itself, the model has two two spaces. There's what we call physical space, which is the space that accommodates the stretching. But we also have the transform space, or what I would call the computational space, in which the data will be mapped into. So the computational space in the transform or computational space, we have regular grid. But in the physical grid, we have the stretch grid. So what the model does is that it maps information from the physical to the transform space, which is called computational space, using a series of grid geometry with a lot of mathematics. So, and the advantage of this, one, it helps us to minimize numerical error. Then it helps us to extract all the diagnostic that we will need. And then we also, it's very good. I mean, it helps in increasing the stretching sharply without any spurious error at the interface. And it also gives a room for the dynamic stretching that I will show later. So these are just some of the information in the model development. So I will show you some of the results that we've obtained with the model. So here is the application of the model over West Africa. This is the grid structure that we use in that experiment. And basically we see that within 0 to 40 degree resolution, the resolution of the model is about 0.5, and it's coarse away from that region. So also along the longitude, the resolution is about 0.5 within this area. So over West Africa, the model has a resolution of about 0 by 0.5, so as to capture the atmospheric features there. So here is the observation showing the precipitation over the entire globe. And here is the model simulation. So we see that the model captures very well the global pattern of precipitation, which is a signature of the global circulation features. And also it resolves all the small scale features in rainfall over the region as we have in the observation. One challenge that many global models have over West Africa is to be able to simulate the features in monsoon system. And one of the features is the vertical ascent. So as we see from this observation, the color shows the vertical motion. The blue means upward motion, while the red means downward motion. So as we see from observation, there are basically three regions of vertical motion. We have one around 10 degrees north. We have another one at 20 degrees north. And in between them, we have the weak ascent. So, and this corresponds to where we have the peak of precipitation over the region, while this is just a dry ascent. So now, but many models, including CAM, which before we introduce the ULAG into it, this is how it depicts this vertical motion. It's unable to split these two assets, as we see in observation. And that means that it's producing precipitation in the wrong location. So instead of giving the maximum precipitation around 10 degrees north, it's actually pitching it between 15 and 20 degrees north, because this vertical asset is in the wrong position. But with CAM ULAG, the model captures it better than what CAM does. So we see the vertical ascent there. So this is CAM ULAG with uniform grid. So we could run the model using stretched or uniform. So when we run it with a uniform grid, and with this we see it captured the location of the precipitation, but at uniform grid is unable to simulate to split that vertical ascent the vertical motion into two, as we see in observation. But as we activate the stretch grid capacity of the model, we see that it's able to reproduce this vertical motion, the splitting into as we have in observation. Although the strength of the second one is weaker than observation, but definitely the result is better than without using the stretch grid. So this is one way, we have demonstrated that the stretch grid helps in improving the simulation over simulation of rainfall and atmospheric system over West Africa. This we show the animation of dynamic grid adaptation with CAM ULAG. So what happens is that the model will start with a uniform grid. Then over this box is going to wait for a system that has a vorticity of a particular threshold, really vorticity of that threshold. Then it will follow the system with time. So I don't know where the simulation is, but we can start. So now it's waiting for the system. It picks it there. And then you see the grid resolution is increasing following the system that it has captured. So it's low here, but it keeps following it until it loses it. So that's one of the way we have demonstrated the dynamic grid adaptation in a CAM ULAG. So we've also applied this model over Southern Africa. One of our PhD students called Penny Driver applied it to study the precipitation over Southern Africa, and also see how well the model links the precipitation to the drivers of rainfall over the region. Here, so this is the setup of the model for the Southern African experiment. The high resolution is over Southern Africa, even though it still covers the entire globe. And this is the precipitation, average precipitation over this region, just to show how well the model captured the internal variability of the precipitation over Southern Africa. And we see the model is not doing a bad job in that regard. The correlation between observation and model simulation is around 0.6. So obviously there is still room for improvement for the model, but then generally it captures the internal variability very well, except from years that he actually misses the sign of internal variability. And talking about the driver of the precipitation over Southern Africa, these are the dominant drivers. We have ENSO, we have IOD, that's Indian Ocean Dipole, and then we have Benguela El Nino. So this shows the correlation between those drivers and precipitation over Southern Africa. So this is from observation, crew observation, and this is what the model produced. And you see that it captures the correlation very well, though there are some biases in some region, but in general, the model shows that it's able to link the precipitation with the teleconnections, the drivers. Then we've also applied the model to study the characteristic of tropical cyclone over the Southwest Indian Ocean. As one of the paper from our master student, Mao Yi, which he applies the structure of the grid of the model it used. And basically from the work, he showed that the model could realistically simulate the genesis location of the tropical cyclone, which is in red. This is observation. This is what we call reanalysis. Reanalysis is a combination of model and observation. And this is the CAM-ULAG results. So we even see that the CAM-ULAG result looks even closer to the observation than the reanalysis. However, the model could overestimate the genesis of tropical cyclone over that area. Here we see the track of the tropical cyclone. When they start, what track do they follow? This is what the observation says. This is what the reanalysis says, and that's what the CAM-ULAG is able to do, which agrees well with observation, although there are some discrepancies, especially over the Mozambique. Then this also shows the monthly occurrence of tropical cyclone over the Southwest Indian Ocean. This is what observation shows, and this is the model result, reanalysis in the middle. There are some times that the model underestimates the number, but then it also had capability to overestimate it, especially in January to April. But generally, it captured the trend, the variation, the structure of the monthly variation. Another important thing we look at when we want to evaluate the capability of a model in simulating tropical cyclone is that we look at the wind speed pressure relationship in the model, and we compare with observation. That is the relationship between the wind speed and the mean sea level pressure of the tropical cyclone. The orange line shows what observation is saying. The blue is from the CAM-ULAG, while the action one is from the reanalysis. And the conclusion from this is that the model seems to capture even that relationship better than what the reanalysis gives. So that's all with the CAM-ULAG. But then we also apply other models to do some specific studies. For example, we applied the regional climate model to study how we can use forestation to mitigate impact of global warming in Africa. And on this project, we've published 6 papers. Those are the publications. So, but I'll just highlight the importance results from the most important result from the studies. In that study, in the experiment, I mean, we know that there are a lot of activities to mitigate, to reduce the impact of global warming regionally. So one of the activity that is going on is the planting of trees. So there's the idea that if we plant trees, the trees could help us, it could absorb the CO2 and store it in the soil. But what people usually overlook is the impact, the regional impact, the physical impact of trees in the region. The emphasis is on the chemical impact, but then it also has a regional impact because trees, apart from sequestering CO2, it also has the capability to alter the regional dynamics climate over the where we are planting it, even in the surrounding. And that's what we demonstrated in this experiment. So in that experiment, we set up this model called REGCM. This is the land use characteristic over West Africa, the region of interest. And the idea is to replicate the activity that is going on that was proposed then, that they actually want to plant trees over a tree belt in Savannah or in Sahel. So the question is, what is the best location for this tree, for this exercise? So in our simulation, we tried planting trees over that belt. That's between 8 and 10 zone. We call it planting it in the Savannah region, or should we plant it in the Sahel? So we tested these two options and then look at the climatic impact of planting this tree in those two zones. So here is the result. So the green line, the green box shows where the trees are. Then while the color shows the impact on temperature and on heat wave. So in other words, the change that we experience by planting trees over the region indicated here. So with the panel here, we see that as expected, planting trees in the zone, that is in Sahel, actually reduces the temperature over that region drastically, okay? But if you plant it in Savannah, it reduces the temperature over the region that we have planted the tree, but the model shows that it might increase the temperature north of the region, meaning that it will be adding to the problem of global warming north of the region. And when we investigated this, we see that the reason is because the planting of the tree actually weakens the temperature gradient between land and ocean, and that it weakens the monsoon circulation, which brings moisture into the system. So the monsoon system delays. So it delays in transporting moist and cool air from ocean into the continent. So before it comes, so this region might experience a warmer condition. So this is how it also translates to extreme events like heat wave. So we see that region is projected to, if you plant trees, it actually increase the frequency of heat wave over that region. So similar result for precipitation. With precipitation, it increases precipitation over the region, but for this case, but south of the region, there will be a decrease in precipitation. All the science behind that discussed in the work. But if you plant it here, it increases the precipitation here, but outside the region, there's a opposite effect. And this is how it translates to drought as well. This is the frequency of drought. So the conclusion from this study is that we can't just plant the trees anywhere. We need to know the consequence of planting it in a particular place, and then we weigh the chemical benefit of planting the tree with the physical benefit of it. So another one is we have also studied the cutoff flow, simulating the cutoff flow over influence cutoff flow and precipitation over Western Cape, and these are some of the publications from the work. So in this study, we identified all the cutoff flows for a given period, and then we classified them into groups based on the precipitation they produce. So we classified them into 9 groups, 9 patterns that we see here. And one of the interesting things that we see is that it's not all the cutoff flow that actually produce precipitation over the Western Cape. This is interesting because cutoff flow is known for heavy precipitation over the region. And the moment weather forecast, the moment they see the map, the cutoff flow map approaching the Western Cape, they normally go to issue and we normally go to issue a forecast that, oh, there may be heavy precipitation over the region. And we've seen that sometimes the forecasts do not actually materialize as we thought. And the reason is that it's not all the cutoff load that produces, it's not all the cutoff load that produce a precipitation over the region. So we investigated this and we saw it in the analysis. And then we now say, okay, what are the characteristics? What is the difference between the cutoff load that produces heavy precipitation over this region versus the one that produces weak precipitation? And what we found out is the moisture is very, very important. So the moisture that the cutoff load uses to produce precipitation over this region actually comes from the tropics. And the system has to organize such that it continues to channel that moisture towards the Western Cape versus the one, but if there's no channeling of that moisture, as we see in this case, the cutoff low may not actually produce precipitation. And we have a lot of cases like this, that we have the cutoff low form, but without any precipitation. And we also studied applied some of the model to look at the remote sources of pollutants over Cape Town. We know that Cape Town is one of the, is polluted. But when one look at this pollution and studies it, one may see that the source of the pollution may not all be local. So from this work, we shown that we try to identify different sources of the remote sources of pollution over the region. So what we did, we identified episode days in our simulations, and then we try to map out where the pollutants are coming from. So in this study where we show that the transport of NOx, nitric acid, could actually be all the way from Mpumalanga towards Western Cape, and the system is transferred along the coast towards Cape Town. And we show the vertical structure to see that we have inversion that suppresses it and pushes the pollutant towards this edge, and then it's transported along the coast towards Southern Africa. Here we also show that the PM10 transport could also come from Namibia, something. So in that simulation.
Dr. Patunde, we are
yes,
over time now.
Okay, so lastly, just to show that the CHPC has really helped us in our studies. This is my last slide. So far, it has helped us in publishing a series of papers and graduated students. So thank you.
Okay, thank you. Thank you for the talk. I see there are no questions on the Q&A. So, oh, I think there's one question. I'll take one question. It's from Queen Reynolds. I'm not sure if you can see it, Doctor, or must I read it for you?
Please read it. I can see it.
Okay. The attendee is saying that, thank you for an interesting presentation, Prof. Has there been any work done on using local mesh refinement techniques other than grid stretching? Methods such as cell subdivision are able to handle very general refinement topologies, for example.
Yes, people have done that. There are a lot of work also in that area that people are using the local refinement. The main challenge with that approach is that this local refinement, if it's done dynamically, for example, that may be increasing the computational cost. So because it may not make the simulation to be the parallel something to be optimized, because when you want to start your simulation, you know the number of grid, then you divide it equally among the nodes that you have. But if you have this local refinement with time goes on, some nodes may be having higher more nodes than more grid points than the others. But to answer your question, yes, we also use that as well.
Okay, thank you. Our next speaker for this session would be Professor Giuseppe Pelican from University of KwaZulu-Natal, and he'll be covering under the topic of artificial and morphological phase transitions in polymeric materials. Over to you, Professor.
Good morning. Thank you for the nice introduction. And I would like to thank you and the organizer for giving me the opportunity to be with you today. So this is the title of my talk. And before getting into it, just let me tell you a few details about myself. I hold an honorary position as a associate professor in the School of Chemistry and Physics at the University of KwaZulu-Natal. And these are some a bit outdated but still nice pics of my research group with the Colin Webb Hall in the background of the Peter Meisel campus. UKZN is one of the main research-intensive South African universities, and it comes from the 1994 fusion of the University of Natal that was built in 1910 in Peter Meisel, and the University of Durban Westville, which was known as the University College for Indians in Durban Bay. So I divided my presentation in two parts. In the first one, I'm going to discuss some results we obtained for coarse-grained models of linear cyclic polymer blends. And in the second part, I'm showing you some recent results we obtained for MIG-to-ARM star polymer films. So here there are some details about the computational software and hardware that we used, and also about the computational effort. The molecular dynamics code we used was LAMPS, that was run on single nodes with 24 CPU cores. For both the two systems, the size is similar and approximately equal to 100,000 beads, but typical simulation for linear cyclic polymers lasted longer on average than MIG-to-ARM polymers because they are a mixture of two different molecular species. And in our case, topological interactions tend to make the incubation time longer. Also, the number of parameters to be investigated is considerably larger. So we need at least 2-3 times the number of simulations we used for MIG-to-ARM polymers. Storage needs depends on the data we need to dump, and range between 1 to 10 gigabytes per simulation run. Now let me go on with the scientific business. The focus of this research is on understanding the effect of polymer topology and confinement in the spatial organization of microscopic system. So it can be relevant to cellular systems where the intrinsic topological constraints of cyclic polymers, which include non-knotting and non-concatenation, are present in the so-called chromatin polymer models, and where DNA, RNA can be viewed as a string of beads, with each bead representing a single nucleotide or amino acid monomer, and all these beads are linked together through covalent chemical bonds to form a very long chain. So these models apply physics-based approaches that highlight the importance of entropy for understanding nuclear organization. Techniques for surface modification of plastics are very important in modern technology, and they can be chemical, in which chemical reaction are used to transform the surface layer, or physical, when surface active agents are placed at the surface and allow it to self-assemble. Now, if we focus our attention on the second approach, we easily realize that many important thermoplastics are actually blends, and there is considerable interest into the extent the composition of the blend at the surface differs from that in the bulk in the case of molten polymer mixtures. Obviously, to maintain excellent mechanical properties, it is mandatory that the blend stays in a single phase and no macroscopic phase segregation occurs. In order to reach a better microscopic understanding of the processes which drive this deviation of the density of the surface layer from the bulk, polymers with the same repeat chemistry but different architecture are particularly suited candidates, as we should try to better understand in the next slide. While a number of previous studies focused on how polymer diffusion is affected by polymer topology, the role of chain architecture and molecular mass in determining the polymer species that is going to get preferentially absorbed at the interface is not yet well understood. So by focusing on this aspect, we try to understand the interplay of entropy factors such as the architecture and molecular weight of the polymers and enthalpy factors to the different cohesive energy of the two polymer species in determining which species is more enriched at the surface. So consider polymers with the same chemistry and different architecture, such as linear and cyclic polymers, allows one to better understand the role of conformational entropy, and as we shall see later, also other forms of entropy. The focus of these results I'm going to present is on low energy surfaces, such as vacuum or air, where the polymer species with the lowest cohesive energy density, or if you want, with the lower solubility, is generally favored, since the potential energy cost of separating the melt and producing a surface becomes minimized. So in a recent experimental work, by considering polystyrene polymers with the linear and cyclic architecture, these authors showed the evidence of enhancement of linear polymers at the interface and corresponding depletion of cyclic polymers in the regime of low cyclic polymer composition. Motivated by this work, we performed extensive molecular dynamic simulation of bead spring models of linear cyclic polymers, where Stokes and Brownian forces are considered in acting on polymer beads, so to simulate the effect of the solvent, and polymer beads are interacting among themselves with the Lennard-Jones 12-6 potential. Periodic boundary conditions were applied along the X and Y directions of the simulation box, while at low and high Z, polymers get exposed to empty space and two vacuum blend interface become formed. So we tried to find the evidence of the smoking gun in the regime of low cyclic polymer composition, as it was suggested by the experiments, and we found it. In these plots, the local composition along the box slides in the Z direction is divided by the bulk composition set up in the box, and show that for small degrees of polymerization, linear polymers are more absorbed at the low and high Z surfaces. When we consider the case of longer chain, this time cyclic polymers get more absorbed at the interface, and for all the composition of the mixture, as is shown in this slide, in quite agreement with the prediction of the self-consistent field theory. In this slide, the full lines are for the density profile for the linear polymers, while the dashed lines are for the cyclic polymers. So here we look at the reduced density as the ratio between the number density of the two polymer species and their density far away from the interface, which is what we call the bulk density. On the abscissa, as usual, we plotted the distance from the interface. That is the reason the quantity reported here, the curves reported here, they all tend towards 1 at long distances far away from the interface. So in this figure, the reduced density nearby the interface becomes more enhanced, especially at low compositions where the experiment have been performed. So I would like to briefly mention that very recently, this behavior has been shown experimentally by other authors in a beautiful paper that was published on the Physical Review Letters. Finally, in this table, the average local composition calculated nearby the two interfaces as a function of chain length, they summarize our main finding. Linear polymers enrich the surface in the case of short chains, while the opposite happens in the limit of long chains. This evidence of enhancement of linear polymers in the short chain regime agrees with what was recently reported in experiments which were conducted on linear cyclic polystyrene blends. The molecular mass of the two polymers used in those experiments correspond to roughly 10 to 13 beads per polymer by using the bead spring model with some assumption on the value of the entanglement length. The threshold chain length separating enhancement of linear versus cyclic chains is located between 30 to 50 beads per polymer, in agreement with what we found in the case of low cyclic compositions. That in the case of polystyrene corresponds to a molecular weight of roughly 6,000 to 10,000 grams per mole. Also, this prediction for the threshold in agreement with the recent experiments conducted on polystyrene polymers. And now what we can do, we can try to have more insight into this behavior by looking at some quantities in the next few slides. When we try to find an explanation for this composition and density enhancement at the interface, it is important to have a look at a paper by Wu and Fredrickson, where they used the so-called self-consistent field theory, which is essentially a linear response theory. And by using this theory, they showed that there are some surface potentials of entropic origin, which are formed by the presence of chain ends of open polymers, such as linear polymers. Essentially, these authors suggest that polymer endpoints are sticky, attractive, and what makes their work even more interesting is that these potential of entropic origin have been measured very recently by other authors using neutron reflectometry and Raman spectroscopy to study linear and branched polymer blends of PMMA, polymethyl methacrylate. So we had a look at the instantaneous histogram targeting chain ends and how results seem to corroborate that chain ends get preferentially absorbed at the interface. What we know is that the higher concentration of chain ends is found in the case of longer chains, while the percentage of linear polymers enriching the interface is almost the same, is almost unaltered. In this slide, what we do, we look at a simple parameter that is directly linked to polymer flexibility and conformational entropy. And this parameter is the radius of gyration, and we calculated it as a function of the distance from the interface. Even in this case, there are some evident differences between short and long chains. The radius of gyration gets smaller as the interface approaches, which means that the polymers get more forward and lose conformational entropy in both the two cases. However, if you look at the panel on the left, you see that for short chains, the trend is very similar. Why? And the cyclic polymer get just a bit more forward than linear polymers. While for long chains, look at the panel on the right, the greater linear polymer flexibility allows them to fold more efficiently at the interface in comparison to cyclic polymers. Here we show the total energy per bead of the two polymer species as a function of the distance from the interface. And the total energy per bead is clearly higher for cyclic polymers across the whole range of distances from the interface. In the case of short chains, look at the panel on the left. Since cyclic polymers are much less flexible than linear polymers at small degrees of polymerization, they pack less efficiently and achieve a less than optimal number of pair interactions among their beads. This aspect shows the severe constraint imposed on the flexibility of cyclic polymers by the loop topology when their chain length is small. In other words, we may say that the lack of flexibility of cyclic polymers, as determined by the loop topology, when the chain length is small, is a tight constraint, and it affects their tendency to move towards the surface. So let's try to summarize the result that we showed in terms of entropic and enthalpy contributions to the free energy of the system. At low degrees of polymerization, when cyclic polymers reach the surface, their conformational entropy decreases because of their faulting. For the same reason, for being partially in contact with the empty space, also their energy decreases. So at the interface, linear and cyclic polymers should get a similar loss of conformational entropy when we consider short chains. However, the entropy overall increases because chain ends at the interface had a positive entropic contribution, which favors linear polymer enhancement at the interface. In a similar way, a linear solution at the interface becomes favored because they have a smaller energy per bit. So in this scenario, the linear enhancement that we observe at the interface, in the case of short chains, is the result of an entropy-mediated process where entropy also plays an important role. On the contrary, when we consider long chains, we observe that cyclic polymers fold less than linear ones, so they lose less conformational entropy. So even if linear polymers can enhance the entropy to their chain ends, the entropy balance is likely to favor cyclic polymers at the interface. So the cyclic enhancement for long chain lengths emerges as a genuine entropic process, which is driven once again by the presence of the loop geometry, preventing cyclic chains at the interface from folding as efficiently as linear chains. In summary, I think that we were able to explain what's going on in terms of these two contributions of entropy and enthalpy to the interfacial free energy of the system. So now we can move to the next subject, which is MIG-to-ARM star polymers. This polymer is a very special type of polymer with at least two distinct types of chains attached to a common center. Due to their novel architectures, MSPs, so let's use the acronym MSPs to indicate MIG-to-ARM star polymers, can self-assemble into nanostructure with emergent physical and chemical properties like micelles and other interesting structures. So the main purpose of our work was to gain a fundamental understanding of the effect of solvent quality and substrate details on the final morphology, the domain size, and the ordering in these solvent-swollen MSP thin films. So in our simulations, we used a 4-arm model for these MSPs. So by using the general formula, it is AN2, CBN2. The central bead, the C bead, and the beads of the two arms, A, are considered as high swelling beads, and we will call them with the acronym HSB. Whereas beads of the other two arms, beads of the B type, are the so-called low swelling beads, and we will refer to them as LSB beads. Okay, the solvent is referred as Sol or type 1, and is modeled as single monomers with the total number of beads corresponding to a swelling ratio approximately equal to 2, where the swelling ratio is defined as the number of solvent beads to the number of HSB beads. So interaction between different types of non-bonded beads are calculated by using again the 12-6 Lennard-Jones potential. We are still using the bead spring models for the polymers, and the list of parameters, so Lennard-Jones parameters for different cohesive and pairwise interactions, so are shown in this. The list is shown in this line, in this table. The purpose of varying Sol LSB interaction parameter, the parameter epsilon 1, 2, while keeping the other interaction parameter fixed, is to focus only on the effect of quality of the solvent on the morphology of the simulated systems. So the interaction potential of all beads with the substrate are also modeled by Lennard-Jones potential. However, the strength of interaction of different blocks with the substrate varies depending on the weighting preference of the substrate. We made use of a strong substrate HSB interaction energy, as you can see in this table, which is equivalent to a strong hydrogen bonding interaction between HSB block and the substrate. Solvent substrate and LSB substrate pair interactions are considered to be purely repulsive to make the substrate strongly selecting to the swelling block only, that is the HSB block. So here we show the cases in the neighborhood of the morphological transition in going from a value of the LSB Sol interaction parameter of 0.85 to 0.95. So in going from 0.85 to 0.95, we move from a poor to a good solvent. And we can see the change from cylindrical to lamellar morphology as the quality of the solvent changes to good, while the solvent is kept as a good solvent for the other block, because this is for just one of the two blocks. If we look at this slide, classically, the morphology of block copolymers is controlled by the volume fraction of the various blocks. So in our study, we consider a symmetric block copolymer, and in absence of solvent, we expect it to form a lamellar type of morphology. So the solvent plays an important role and it virtually changes the volume fractions of the two blocks. In this slide, I'm showing two-dimensional snapshots of equilibrated morphology of MSP films, including solvent. And this is done for poor solvent on the left and good solvent conditions on the right. In the case of poor solvent, look at the panel on the left, it is clear that the solvent beads are abundant only within the regions occupied by HSB beads, since they prefer to interact with themselves and HSB beads at these energetic conditions. Our conclusion is that for poor solvent conditions, the volume fraction of HSB is dominant over that of LSB, which leads to the cylindrical arrangement of LSB beads that we've shown before. Now, to get a better understanding of the distribution of solvent in the LSB and HSB domains, the number density profile of the two different types of beads, of the three different types of beads, Sol, HSB, and LSB, is considered different values of epsilon 1, 2, as you can see in this figure. Two different kind of density profiles are shown for the cylindrical morphology cases to clearly illustrate the distribution of the solvent in the blocks. See the panel on the top left, panel A, and also the distribution of the different beads with respect to the substrate. Look at panel B on the top right. So the number density profile with respect to the substrate surface, as shown in panels B and D on the right part of this slide, they display several interesting features. The HSB layer near the substrate for all cases characterized by a solvent-free HSB monolayer, which is adjacent to a swollen HSB domain, due to the fact that the substrate is highly selective to the HSB block, but it is repulsive to the solvent and to the LSB block. Above this first layer, I don't know if you can see that, order patterns of alternating domains, which are preferably filled by beads of the same type, they clearly emerge. And the density profiles as a function of the distance from the interface are shown again in panels B and D. They are very informative in explaining how the phase transition from cylindrical to lamellar morphology takes place as the solvent quality changes from poor to good. Our conclusion is that the quality of as the quality of solvent increases, the cylindrical morphology at those peak locations deform into elliptic cylinders with the larger radius parallel to the substrate, and finally evolve to a lamellar kind of morphology in a good solvent. So I think that I can try to draw some conclusions, varying the solvent block relative interaction parameter, the parameter epsilon 1, 2. We clearly show that the morphology of the simulated system becomes significantly affected. The spatial distribution of solvent beads within the simulation box has also been highly influenced by heat. In particular, in the present work, systematically changing the interaction strength between one block of the MIC-2 polymers and the solvent, while keeping the remaining different types of interaction parameters constant, resulted in morphological transition from a lamellar to a cylindrical morphology for a system that is intrinsically, inherently lamellar in the absence of solvent. These morphological transitions are somehow directly linked to the unbalanced distribution of solvent beads throughout the film, causing one block to behave like a minority phase and form a cylindrical morphology. So these are some of the people I would like to acknowledge. There is a former PhD student of mine, Dr. Francis Gaito, who works currently as a senior lecturer at the Masinde Muliro University of Science and Technology in Kenya. And then there are Professor Zeyn Workine of the Bahir Dar University in Ethiopia, and Professor Mesfin Sige of the University of Akron in the USA. So I would like to thank you for your attention, and these are some of the papers that we published in the last few years as related to this project. Thank you for your attention.
All right, thank you, Professor. I think I've got one question for you today. I'm gonna read it for you. So Queen Reynolds is saying that, thank you for a fascinating talk, Prof. Have you done any simulations combining linear, cyclic, and MSP polymers in the same mixture, or are their systems completely different chemically?
Well, potentially, this is a possibility. That is a possibility for sure, because what we are doing here, we are just using a coarse grain model. We are using a bead spring model where you can imagine all these coarse grained beads representing some functional groups of the polymers linked via bonding potentials like the Fini potential. So in this picture, since we are using essentially the same model, bead spring models for linear, cyclic, and for MSPs, it would be feasible for us to mix all of them together. That is a possibility. We did not try that because I'm not sure what kind of relevance that kind of study would have, but it is an interesting question. So thank you for asking it.
Thank you, Professor. That was the only question that we have. I think we are done for the session. Thank you to the speakers and all attendees. And just a reminder, the recordings and presentations will be shared after this conference. Thank you.
Thank you. Bye-bye.